Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Sunny Wong with us today. Hello, Sunny.
Hello, Frank. Thank you for having me.
You are outside.
Yes.
That is rare. Most people do these inside. That's very cool. Where are you located at, Sunny? What's your geolocation there?
Yeah, I'm at Santa Barbara. I'm doing my 5th year of PhD here. And we just had a storm this weekend, but it's usually sunny out here, and it is today. That's why I decided to come out here and enjoy some sunshine.
Very lovely. Very lovely. And I'll pick up on that other part. Do you anticipate graduating this year?
No, I'll be doing a 6th year, and then I'll be applying to postdocs basically this fall.
Okay. Okay. Well, I'll still give it an early Dr. Wong. So very good. And Sunny, what do you like to do for research?
Yeah, so I'm generally interested in binary stars, and in particular binary stars with at least one white dwarf. So far, all my projects have involved some sort of like either the interactions between a white dwarf and another star, a helium-rich star, and sometimes it involves like what the aftermath is. So when you have two white dwarfs are interacting with each other, they undergo mass transfer, and sometimes you get an explosion. One of them explodes as a Type 1a supernova. But in the case where the explosion doesn't happen, then the two white dwarfs merge, and you get a star that's called an Argomore star, which is the topic of
Today.
our paper today.
Yes. Cool. Very cool. And that will bring us to this very lovely APJ article. It is open access. It's the open access era, people. Go get a copy. The Asteroseismological Richness of RCB and dLHdC stars. And Sunny, take us away.
Okay. So first I want to shout out to my co-author Lars Wilson, who is my PhD advisor. Has been a great advisor. He's very knowledgeable, but also one of the nicest people I've met in the field. He's very insightful. This whole paper actually started as an idea that he came up with. So we were first approached by Viraj Puram-Malcolm from Caltech. He's doing his PhD at Caltech there. He's studying the pulsations of Markov-4 stars, or sometimes the dustless HDC stars.
Okay.
And he approached us and asked us, where do these pulsations come from? So Lars thought about it. There's been some papers over the last 2 to 3 decades about these pulsations being driven by what's called the strange mode instability, which happens when you have a star that's very highly radiation pressure dominated. But Lars looked at the structure of the Argomore stars. So these Argomore stars have a big, puffy convective envelope.
Yes. Okay.
And one thing that we know about stars with convective envelopes is that they exhibit what's called the solar-like oscillations.
Okay.
So solar-like oscillations are oscillations that we first observe in the sun. The sun has a convective envelope, and these convective motions drive pulsations in the form of P modes, which are acoustic waves in the atmosphere.
Okay.
And we see, yeah, and that's the pulsations that we see in the sun. And later it's found that you can extend this to a lot of other different stars, including subgiants and red giants, all of which have big convective envelopes.
Yeah.
And whenever you see these, you see the same characteristic pulsations, which turn out to be the same phenomenon. And so Lars thought about that, and he compares the structure between Argomore stars and subgiants and red giants.
Okay.
And he starts thinking, what if the Argomore pulsations are solar-like oscillations? And that's the whole idea of the paper, is just to point out the idea that Archer-Bohr pulsations might be solar-like oscillations.
Cool. Got it. Very good.
But first, but I want to take a step back and talk about what Archer-Bohr stars are, because not everyone knows what Archer-Bohr stars are. So Archer-Bohr stars are named after the stereotypical star, our Corona Borealis. It's a star inside the constellation Corona Borealis. And in all constellations, the R designation stands for the most variable star. So it was known for hundreds of years that our Corona Borealis is a highly variable star. And turns out what's happening is that this is a star that has a very dusty envelope. And when it ejects dust plumes along our line of sight, it rapidly dims, and that causes the sometimes up to 9 magnitude drops in brightness that we observe.
Okay.
And when we look at, so currently there are something like 100 similar Archer-Bohr stars.
Okay.
And when we look at their composition, we find that they have slightly weird composition compared to other stars. So the first thing is that they're hydrogen deficient. There's almost no hydrogen there. So it's mostly helium dominated, but they're also very carbon rich. That's why they have these dust ejection episodes. And then the third thing is that if you compare the oxygen 18 to oxygen 16 ratio, they are more oxygen 18 rich. So the idea is that these oxygen 18 comes from partial helium burning.
Yes. Okay.
And the formation channel for this is that you have two white dwarfs, a carbon-oxygen white dwarf and a helium white dwarf, that are merging together. The helium white dwarf gets accreted onto the carbon-oxygen white dwarf, and there's helium burning at the base of the helium envelope. And all that burning produces a little bit more carbon and also oxygen 18 that gets transported out to the envelope. And that's what's causing the strange composition that we see in Archer-Bohr stars.
Okay.
So this is one funny way where my PhD thesis has taken me.
Okay.
So this is the track where if during mass transfer, one of the stars doesn't explode, they merge together and form one single object. And in this case, it's a Archer-Bohr star.
Got it. Cool. Very cool. Okay.
So in between these dust ejection episodes, we also see that they fluctuate in brightness. The one idea is that these are due to convective motion in the envelope. So we're seeing the eddy turning over in the envelope, which is something that we can't really address with our 1D models. But the other idea is that these are pulsations in the atmosphere. And so, and the typical time scale is somewhere between 30 and up to more than 100 days.
Oh.
A lot of them have timescales of around 30 to 50 days. Okay, so these are the observational facts. And there's one more, which is that when they pulsate, we think it's pulsations. Let's assume that for the sake of this paper.
Okay.
The semi-amplitude is something like 0.1 magnitude.
Oh, okay.
So quite large amplitudes.
Yes. Yes. Indeed. Yes. Okay, cool. I'm with you.
Yep. Okay. So so in our paper, we argue that Archer-Bohr stars, their pulsations are driven by solar-like oscillations. So the first thing you can do is to compare that with normal hydrogen-rich solar-like oscillations. So for typical solar-like oscillations, there's a very well-known relation in the peak of the oscillation power. It's called the frequency of maximum power.
Newmax.
Newmax. Yep.
Yes, here we go. Newmax notation. Okay.
Yeah. So it scales like the sound speed over the pressure scale heights in the photosphere. And in order to try to make use of the solar-like phenomenon to Arco-Bohr stars, we need to make actually one correction, namely that in Arco-Bohr stars, the main composition is not hydrogen-rich, it's helium-rich. So that gives you a factor of 2 in the, factor of 4 in the mean molecular weight.
Yeah.
And that causes a factor of 2 difference in the frequency for maximum power.
Okay.
So that's what equation 1 is trying to show, where we just simply scale the solar-like oscillations for hydrogen-rich stars by a factor of 2 to account for the fact that Arco-Bohr stars have helium-rich envelopes.
Gotcha.
And once you correct that, you find that the frequency for maximum power corresponds to a period of something like 30 days,
Okay.
which is quite in the ballpark of the observed range of Arco-Bohr stars. So that's check number 1.
Tantalizing. Okay, good check. Okay. And then delta nu.
Okay. And then check number 2 is that it's kind of like towards the end of the paper, but so for solar-like oscillations for hydrogen-rich stars, we also know that there's a relation between their luminosity and the assembly amplitude of their pulsations.
Okay.
The more luminous they are, the larger the amplitudes are.
Okay.
And so if you, we know that Arco-Bohr stars have a luminosity of something like 10 to 3, 10 to 4 solar luminosity.
Okay.
And so if you compare hydrogen-rich stars with similar luminosity, these would correspond to a bit near the tip of the red giant branch or even brighter. And for those stars, we know that the oscillation semi-amplitude is something like 0.1 magnitude, which is comparable to what we see for Arco-Bohr stars.
Yes.
So that's check number 2.
Okay.
So these are both encouraging arguments for why we think that Arco-Bohr pulsations might be solar-like oscillations.
Yes, things are pointing in the right direction.
Yeah. And so now we try to make some models and see what kind of pulsation periods we would get. So we use the stellar evolution code, MESA, to make Arco-Bohr models. So I want to shout out to Josiah Schwab, Amber Lauer, Courtney Crawford, and Bradley Munson. They're all pioneers in making Arco-Bohr models inside of MESA. So the whole idea is that you first make a carbon-oxygen core, and then dump some helium on some thick helium envelope onto it. And then you also need to inject some entropy to make the envelope puff up. So that's all like simulating the aftermath of the merger process.
Okay.
So right after the merger products now will puff up and start helium burning. And so that's, and then during the helium burning, the helium shell burning process is when the Arco-Bohr lifetime is. So so let's now go to figure 1.
Take a look at figure 1, and we're going to pull some figure 1. Okay, there we go.
So the left plot is the Hertzsprung-Russell diagram for a Arco-Bohr star model that we made, where we accrete 0.2 solar masses of helium onto a 0.5 solar mass carbon-oxygen core.
Okay.
And then for the envelope composition, we make it slightly carbon rich because we think that there's been some mixing during the merger process.
Mm-hmm.
And we simply use observational abundances. Well, we simply scale our stellar model to observed abundances.
Mm-hmm.
Um, and then in here, you see the model track in blue. So it starts from the right-hand side and then continues on the left-hand side.
Yes.
So the initial dip is because the star is still thermally adjusting to, yeah, right after the merger process.
Okay.
And then afterwards, it gradually brightens
Mm-hmm.
because its carbon core gets more massive as the helium gets burned.
Got it. Okay. I'm with you. Uh-huh.
Yeah. So yeah, and then all the gray points here are points of equal lifetimes.
Oh,
So
very good. Okay.
yeah, what it's really showing is that most of them spend a lot of their lifetime doing shell burning around 5 to 6,000 Kelvin.
Yes. Uh-huh.
And then the lifetime towards the blue is a bit shorter. Though I should say this is a model without any mass loss.
Okay.
Of course, we'll show a model with mass loss later on.
And what are the two orange triangles?
Great question. So for these two orange triangles, we try to look at the stellar profile in more detail
Ah,
to see what we'll look at the propagation diagram to see
so,
how
okay.
the modes, to see where the modes propagate. So that's something I'll mention later in the second figure.
Okay.
So so far so good.
Yep, I'm with you. So far, so good.
Okay. So along this Larva 4 evolution model, at each point, we try to compute the oscillation frequencies
Okay.
with the with gyrate.
Okay.
And the way we do that is kind of interesting. So we cut out the core so that we're not getting any G modes from the core.
Okay.
Because there are so many G modes in the core, so it's like a very computationally expensive game to play. So instead,
Yes.
we cut out the core so that we only are looking at the P modes in the envelope.
Okay.
Uh,
Okay.
yeah, and then the plot on the right-hand side
Yeah.
shows the periods of the P modes that we find for the envelope, where the different colors indicate different angular degrees.
Yeah.
L
Okay.
of 0, 1, and 2.
Okay. I'm with you. Uh-huh. Okay.
Yep. Okay, so all of these are different modes that could exist in the envelope. And the it doesn't really tell you where the peak oscillation power should be. And the black line is the scaled new max that we find.
Yes.
So what it's really saying is that you would expect most of the power to come out of n equals 2 or n equals 3
Okay.
modes.
Okay. Yes. Yes. Gotcha. So these are the numbers on the side is principal mode.
Yep. Yep.
Okay. Gotcha. Gotcha. I am with you. Gotcha. Okay.
So okay, and then actually here they're not just P modes. Sometimes we also see G modes. So those are the modes that you see above 100 days.
Up here it is.
Yep.
Yes.
Yeah,
Yes.
there are some G modes that could exist in the envelope because there's sometimes a radiative layer depending on the effective temperature of the model.
Got it.
Okay. So yeah, so these are all the modes, but let's take a look in more details for where the modes would look like
Okay.
in two particular models. Those are the ones in orange on the HR diagram on the
Gotcha.
left.
Okay. So let's go there. That will be figure 2, energy in a mode inertia, define there, and there we go. propagation diagrams. Bang.
Yep. Yeah, so here we picked two stellar profiles at two different times. The one on the left is at a lower effective temperature, and then the one on the right is at a higher effective temperature.
Those 2 points, yes.
And they correspond to the orange points, orange angle points that we saw in the HR diagram here.
Yes.
And so for those who are not familiar, the top two plots are what we call propagation diagrams. It shows, so the x-axis would be the radius, and then y-axis is the frequency.
Okay.
And the region in the blue is a G mode propagation region.
Okay.
So if you have a mode in the blue region, it allows for propagation of a G mode there.
Okay.
Whereas in the region in the orange, it allows for the propagation of a P mode.
Okay.
And then in between the solution is a decaying solution.
Okay.
Okay. So so most of the envelope is convective, and okay. So you don't see any. Sorry, let me back up. So the blue region comes from the core.
Yes.
And then the outside of the blue region is the convective envelope.
Gotcha. Okay.
And most of the modes that you see here, actually all of them are P modes. So the P modes are indicated on the dotted lines.
Okay.
With their N numbers indicated for the first three modes. And then for each of these modes, we also plot their eigenfunction on the bottom plots.
Okay. Okay.
So the n equals 1 just monotonically rising to the surface. The n equals 2, a little dip.
Gotcha. The colors correspond here. Gotcha. I'm with you. Okay. Yes.
Let's see. Okay, so at lower effective temperatures, all the CR P modes, because the entire surface is just convective. But once you go to higher temperatures, now on the right-hand side, you see a second blue region appearing at a radius of around 0.3 to 0.7.
Yes, right here.
That's because the one single convective region now breaks into two convective regions. And in between, there's a radiative region, which allows for the propagation of G modes.
Cool. Okay.
So instead of n equals 1, 2, 3, on top of n equals 1, 2, 3, you also get n equals -1 and -2, which are G mode dominated in the envelope.
Okay.
And so we show a few more plots, a few more eigenfunctions down at the bottom.
Let's see, a few more. -1, -2 is one going off scale, coming back down, making a reappearance. Okay. Okay. I'm good. I'm with you.
Yeah, so the one fun thing about these arcobores is that we find that they not only support P modes in the envelope, but sometimes when there's a radiative region in the envelope, they also support G modes.
Yes, right there to get hot enough. Okay, make a cavity. Cool, very nice.
So these are mainly the modes that are propagating in the envelope. But once you put the core back in, you get a lot more modes because because there are many more G modes that can propagate in the core and can couple to the P or G modes in the envelope.
Yes. Okay.
And that's what the third figure is trying to show.
Okay, so let's go in and throw that core in. These are convective timescales, which we saw in the previous plot. And here we go, mode inertias.
Yeah, so okay, so on the top row, what you're looking at is the mode inertia as a function of the mode frequency.
Mhm.
Here, there are many dots. Each dot is one mode when
Yeah.
we run with gyra, including the core.
Okay.
So
Oh, this is interesting.
yeah, so here you get a lot more modes because we're putting the core back in, which can support a lot more G modes. But
Yeah.
whenever there's a G mode strongly coupled to the P mode in the envelope, you see a dip in the mode inertia.
Okay.
So you see all these combs in the mode inertia,
Mm-hmm.
and at the minimum,
Yes.
it's a P mode that's strongly coupled to the core.
Cool. Very nice. Uh-huh. I understand. Good.
Um,
And what are the what are the pink or purple boxes?
Great question. So when we zoom in, near the most P dominated,
Okay. Gotcha.
we look at the neighboring modes because for G modes, there's an asymptotic relation where neighboring modes would differ only by a constant period.
Okay.
So the bottom plot is trying to show the difference in periods
Mm-hmm.
between the mode at the mode inertia minimum and neighboring modes.
Gotcha. So
Uh,
zoom ins. Okay. Uh-huh. Gotcha.
so
Okay.
yeah, you can see all these modes being separated by a constant period spacing
Mm-hmm.
of
Mm-hmm.
around 10 to minus 4 days.
Okay. Yes. Mhm.
So
Interesting. Here, a little shorter. Okay. Nice. Okay.
So the whole reason we're doing this is that for solar-like oscillations in red giants and subgiants, um, the detection has gone so good where we could detect the period spacing in core G modes.
Okay.
And that has allowed seismologists to probe the core structure of these red giants.
Cool.
And they're even able to distinguish between core burning red giants and also those who have not started the helium flash yet.
Wow. Cool. Okay.
Um, we tried to ask whether we can play the same game for Argo Bohr stars by if we could detect
Yeah.
uh, these G modes in the core,
Okay.
except that it would require us to be able to detect period spacing less than 10 minutes for days,
Okay.
which is a very hard game. So what you need is a long baseline observation
Okay.
of something like 10 years.
Okay. That's a big ask, but okay.
Yeah, so for now it's mainly a theoretical speculation,
Yeah. Okay.
but who knows what's gonna happen in the future?
Stuff happens. Stuff
Yeah.
happens. Okay. Cool. It's always good to have targets to go after, right?
Yep.
Very
Yeah.
good. And I
So
think we end up with one more. Figure four.
yeah, so the first model we showed is a 0.7 solar mass in total,
Uh-huh.
but depending on what kind of helium white dwarfs and carbon oxygen white dwarfs you're merging, you could get different total masses and also different envelope to core ratios.
Yeah.
So we tried to run two more models, one with a higher total mass. That's the blue line in the HR diagram here.
Mm-hmm. Going this way. Yeah.
So this one has a much higher luminosity because its core mass is higher. And then
Yes.
it also, both the starting core mass and the final core mass are higher. So the helium shell burning luminosity is higher.
Okay.
And then we also run a third model where we allow some mass loss from our Caduceus 0.2 plus 0.5 solar mass model.
Green one. Yes.
So this one asymptotes to a much lower luminosity because it loses a fraction of its own. So it's finding mass its mass goes from 0.7 down to like 0.62.
Yes. Okay. I'm with you. Okay. So variations is what we call. Okay.
And for both of these models, we also try to compute the periods um, by, well, the period of the modes that are in the envelope.
Okay.
So these, for the higher mass model, it's the plots on the bottom left.
Yes.
But we show only the modes that are near the frequency for maximum power, because that's where we believe most of the observed modes will be.
Okay. Okay.
Um, yeah, if you plot all the other modes, it's very confusing
Gotcha.
plots.
I'm with you. I see now. Cool.
Whereas the lower mass model will be on the right. So
Yes.
the main difference, the main message in this plot is that when you have a higher mass model, the period is longer, whereas if you have lower mass, the period is shorter.
Okay. Yes. General depression. Same scales here. Okay.
The main reason why we're doing this is that actually Argo-4 stars, the Argo-4 stars that we call in this paper, have two subpopulations. One is the stereotypical Argo-4 star, which have dust ejection episodes.
Okay. Yes.
But turns out there's actually a slightly different version. They have similar spectra, except that they don't show any dust ejection episodes. So these are
Okay.
called the dustless hydrogen deficient stars, dLHdCs. And observationally, we know that they appear less luminous compared to the typical Argo-4 stars.
Okay.
So there's been some suggestion that lower luminosity suggests a lower mass,
Yes.
which we also see in others. And then the other thing, which has not been, I don't think has been put out yet, to my knowledge, is that these dustless hydrogen deficient carbon stars show shorter oscillation periods.
Okay.
So something like between 10 to 30 days.
Okay.
And from our low mass model, we also think that the fact that dustless hydrogen deficient carbon stars show shorter period of
Okay.
oscillation is an indication that they're low mass.
Cool. Cool. Very nice. Okay. Very nice.
So
Sunny. Oh, go ahead.
yeah, so the main message of this paper is number one, to point out that Argo-4 stars, their oscillations could be solar-like oscillation
Yes.
origin because they have big convective envelopes, which are similar to our typical hydrogen-rich stars.
Yes.
And when we apply the scaling, both in effect and in the oscillation period, oscillation semi-amplitudes, they also seem to apply well.
Yeah. Everything's pointing in the right direction here, so it's very good. Very good. Okay. Let's punt on that at the moment. Okay. Very good. Sunny, I want to thank you so much for walking us through your lovely APJ article. Thank you.
Thank you so much for having me.
Sure. And you touched on it a little bit there at the end. And you also mentioned the 10-year baseline. So I'm just curious, where do we go with this research given the published article? Are maybe some of the observational campaigns that are coming up, maybe we'll get 10,000 of these, 100,000 of these kind of stars. Is there additional theoretical work that could be done along these lines on these hydrogen deficient stars in carbon rich? Yeah.
Great question. So on the observational side, I think, the theoretical prediction for the helium white dwarf carbon oxygen white dwarf merger is that we'll see something like 100 to 1,000 in the Milky Way.
Okay.
So we're kind of like almost there. So I don't expect that we'll see too many more. but it would be much better to get a systematic study
Mhm.
to look at the oscillation periods of these Archer-Bohr stars.
Fair.
So one mission that's already up there is TESS.
Yes.
So TESS looks at a sector continuously for 27 days, and then it moves to a different sector. But there are some sectors that are continuously being viewed in, and Archer-Bohr stars and also dustless HDC stars in those continuous viewing zones will be great
Okay.
at looking at detecting different mode periods, and yeah. Okay.
Cool.
So yeah, and especially the dustless hydrogen deficient
Mhm.
carbon stars, because they have shorter mode periods. So it's and also don't show dust ejection episodes, which means that you can always look at their oscillations
Mhm.
with TESS. And TESS's observational length is much better for the dustless HDC stars compared to Archer-Bohr stars.
Okay.
And then let's see. Yeah, so that's on the observational side, I would say that currently let's see. Well, so the purpose of this paper is to kind of stir the pot
Right.
to get astroseismologists maybe consider
Looking.
Archer-Bohr stars as solar-like oscillations.
Mhm.
And perhaps once we detect enough periods, you could try to use the nu max and also actually delta nu. So delta nu is the frequency separation between two modes.
I'm with you.
If you combine those, you could try to measure the mass and radius of the star.
Cool.
That's been applied widely for solar-like oscillations. And we think that once we detect enough mode periods for Archer-Bohr stars with enough resolving power of different modes, then perhaps we can start to look into the structure of these Archer-Bohr stars.
Nice.
And in the very long future, if we have that long of a baseline, maybe also probe into the core structure of these Archer stars.
Really nice.
Big ask, I know.
That would be awesome. Very cool. Very nice. Very nice. Well, I really look forward to seeing this develop over, let's say the next few years to maybe the next 10, maybe. Very cool. It'll be really fun to see it go though. And again, giving targets more predictions is a good thing. So very nice. Sunny, thank you so much for walking us through your very lovely article.
Yeah, thank you so much for having me.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.